So I'm going to go through how to deal with redox titrations. This is going to be a bit long. On a test or quiz, some of these pieces might be shortened, but you need to know how to deal with the whole process. And if you do a redox titration in a lab setting, this is going to go through all the pieces you'd have to do in your analysis to write up a redox titration lab. So we've got a question: determine the concentration of chromium ions. All titrations have an unknown concentration in them. Okay? And then you have to have another chemical that you know the concentration. Okay? And we're going to see that buried down below in our table. We've got another chemical of known concentration. So the first thing you need to do before you can really tackle any of this is you need a balanced chemical equation. Last year, you'd need the balanced acid-base. Now we need the correct redox. So our main strategy is either to use oxidation numbers and predicted or use our table. Okay, and all your redox titration questions within Chem 30, you'll be able to use your table. So you'd want to make a list of all the species you have. Now, I'm not going to write that list out. I'm just going to do it orally, and then I'm going to flip to the reduction table and find of anything written here, what is our best OA and what is our best RA. Okay. So what do we have? We have a standard potassium dichromate. So that's an ionic compound. So I'm going to think of potassium separate from dichromate. Okay, if I was making a list, I'd put those two on the list. We have it acidified, so we have to realize we've got H+, and we've got chromium 2 ions. In solution, so we've got water. So that's all the pieces. We've got potassium, we got dichromate, we got H+, we got chromium 2, and we've got water. And from that, I'm going to grab the best oxidizing agent, the best reducing agent, and I can net up and have my balanced chemical equation. So we've got our Alberta reduction table. And the fastest way to try to get your equation is to start with the strongest and go down till you find what you have. So we have no fluoride or no lead or no permanganate or gold or dichromate. Okay. But once we get down a few rows, I find a pairing that I have. We have dichromate and we have an acidified solution, H+. We don't have any OAs above that, so that's the best one we have. Water is way below it. Potassium ions are way below it. Okay. So I'm going to grab that half reaction. We've already had a lesson on the 5 steps of predicting redox reactions. So I want to go through this part really quickly. The predicting reaction piece. Okay, so that's our best OA. Now we have to keep that list kind of in our mind. The potassium, the dichromate, the H+, the chromium 2, and the water. But I'm going to go to the RA column, start at the bottom, and work my way up. Now I have cut off this table that's in the notes. The strongest reducing agent would be at the bottom, the weakest reducing agent at the very top. And when you go up, water is way up high. We don't have any H+ on the RA sides. There's no dichromate on the RA sides. The best we have is chromium 2 ions. So chromium 2 going backwards makes chromium 3 and an electron. I'm going to stick in 1 electron for emphasis. Okay. So I've shortcutted making a list and finding the 2 winners. Okay. We almost have our net redox reaction. Once I balance the electrons, there are 6 from the OA, and the strongest reducing agent produces 1. So that doesn't balance. I have to multiply the half reaction for the RA by 6. So 6 of those will make 6 of those, and instead of 1, there'll be 6 electrons produced. Okay. So these electrons that are produced are the exact same electrons that are consumed. They're not different electrons. They're the same. They have to balance. You can't spit 6 out and take 5 in. So now I can write our reaction that we're going to do our redox titration and our stoich with. So chromium 2 Cr2O7 2-, aqueous plus 14H plus. So that's my 3 reactants. 2 of them are a combo OA. Then on the product side, this doesn't happen a lot, but we have the same product showing up in both half reactions. So I'm going to add those together. We've got 6 chromium 3s and 2 more. So there's 8 chromium 3 plus. And 7 water. Okay. So we've got an equation, so now we can go back up, read the question, and organize our information. So I'm going to do a bit of scrolling up and down. I'm going to find questions and numbers. Determine the chromium 2 concentration. So that's our goal. Standard potassium dichromate was used to oxidize 10 mils of acidified chromium solution. So look, here's our chromium solution, and this was 10 mils, and it's been acidified. The acid was actually added in with the chromium ions. We must have some more information. Okay. The rest of the information is buried in this table. Potassium dichromate is 0.125 moles per liter. Okay. And we know the volume, or we will know it. We've got all these titrations, and we can get the volume average of dichromate that was used. So this is a titration. We have V initial and V final in a burette. The dichromate was up in a burette. The 10 mil sample of chromium ions was down below in an Erlenmeyer flask. Okay. And he used a pipette to transfer that 10 mils. Okay. So let's get that V average. So a lot of the math's been done for us. Okay. You take the final minus the initial, and you get the volume that was used. Okay. Now this was sort of a perfect titration. All 3 of them were the exact same volume. Okay. To get V average, you add up all your good titrations, and then you divide by how many titrations you did. And because they're all the same, you're going to get that 17.4 as your average. If any of the trials are greater than 0.2 mils from its closest other titration, in Chem 20 and Chem 30, you should exclude those. Some systematic error happened. These are all the same. None of them are more than 0.2. Now, when you're in the lab with me using a burette, you should be recording 2 decimal places, not 1 like we have in this example. Okay. So we have our V average. Okay. It's really important with titrations to collect and organize your data. You don't have to do it the way I'm doing it, but I think it's a great strategy. Write your equation, then organize your information under your reactants so you can really make a good plan. Okay. Okay. So how are we going to solve this? Well, we have to have some chemical that we know the moles. Well, we know the C and V of dichromate. We can use that molar amount to figure out how many moles of chromium 2+ there must be. Our equation tells us for every one of those, there's going to be 6 dichromates. So we can get the moles of the known. We can convert that using our 1 and our 6 coefficients to get moles of what we want to know. And if we know the moles and the volume, we can figure out the concentration. Okay. So there's always these same 3 steps. And this is the math that I'm going to do shortly. You want to get the moles of what I call the known. This is where the C and the V are both known. I put a little check mark under both. You're not figuring them out. They're in the question. Get the moles of known to the moles of the unknown, what you're trying to find out. And this is where you have to do a little stoichiometry, required over given. Okay, probably your last unit of Chem 20. Okay. And then step 3 is the concentration for the unknown. The answer, really, the goal of the whole problem. Okay. Those are the exact same 3 things I would have told my Chem 20s. You could solve these with an ICE table. So depending on your Chem 20 teacher, if they did this in an ICE table and that method works for you, it's the same 3 steps. So 1, what is the moles of the known? What do we know the C and the V? That's our dichromate. So I'm going to get moles of dichromate. Okay. I love when you put in little headings, not just moles, but you tell me what chemical. Okay. Moles is C times V, concentration of dichromate times volume of dichromate, 0.125 moles per liter, and we've got this information right above so we don't make any errors by pulling the wrong volume. Now, moles per liter means we need liter volume. So I'm going to switch those milliliters into liters. I divide it by 1,000. In Chem 20 and 30, we flip between mils and liters a lot. So our moles of dichromate is known. You would keep all the digits in your calculator. So that's our first step done. Our second step is going to use 1 dichromate, requires 6 times more chromium ions. Now I wrote in moles of the chemical to make sure we do the required over given properly. Okay. We're requiring chromium 2+, that's what we want to get, and we know dichromate. Okay. This is going to be our stoich step. The chromium 2 stoichiometric coefficient is a 6, and the dichromate, the given, is a 1. You may not write out those 2 chemicals, all the chemicals I put in here, but you must get the required what you want coefficient on the top, the given on the bottom. Okay. I have not written down every digit in my calculator, but you would leave them all. We're not done. Don't round yet. Okay. You'll round to put on your paper for a quiz, but you'll keep them all in your scientific calculator. Almost done. Concentration, and this is going to be of our chromium 2. is moles per volume, moles per liter. Well, there's the moles of chromium 2. And I know we summarized the volume. There's the volume. So we have the two pieces. So the moles. The volume was 10 milliliters, but we need it in liters, divide by 1,000. We've these 3 zeros after the 1. A pipette has 10.00. There's 4 sig figs. That's why the pipettes are really expensive, that precision to 2 decimal places. So I've kept those trailing 3 zeros. So now I'm at the very, very end. I'm going to round to appropriate significant figures, and we had 3 sig figs in our concentration, 4 in our pipette, 3 in our titration volume. So I'm going to round to 3, 1.31 moles per liter. We're done. We finally answered the question. So this is a nice exemplar for your titration lab. For a test or quiz, I'd probably give you the equation, and then you're just doing step 1, 2, 3, and that should be done in about 3 minutes by the time you've practiced it and you do it on a unit test or diploma. Okay. The balancing and the whole thing is more like a 6-minute question. So that's our redox titration. Now, one thing I flew right through is, how did you know to stop? We've got all these volumes. I never mentioned an indicator. There's no color change mentioned here so far, but I do have a little diagram there. None of those acid-base, phenolphthalein or bromothymol blues, are going to work. They're pH-based. This is OAs reacting with RAs, so they're not going to work. Redox titrations only work if the reactants and products have different colors. So we can see the product show up, and we can see all the reactant go away, and that can tell us to stop. So in this particular example, chromium 2 and 3 are different colors. The H+, the water, has no color. Chromium 2 is your first test tube, and it's more of a bluish green color. And when that reactant runs away, is used up, you're not going to see the blue, and you're just going to see a yellowy type color with the 3+. So in this titration, you would stop when all the blue is gone and it's turned to a yellow. Okay. Okay. If you use clear solutions, it's not going to work. Okay. When we do our titration, we're going to use permanganate and H+, and permanganate is a really dark purple, and it's going to be very obvious when that purple has disappeared or has totally formed in excess. So that's going to guide us. So no indicators to redox titrations. We use the inherent colors of our OAs and RAs to guide us.